For centuries, astronomy has been built upon a simple, elegant binary. On one side, we have stars, engines of creation that fight against gravity using the power of nuclear fusion, lighting up the cold dark of the cosmos. On the other side, we have black holes, engines of destruction, the graveyards of stars where gravity has won the war, crushing matter into infinite density. We were taught that these two objects are separate stages of life. A star lives, it dies, and only then might it become a black hole. They do not coexist, they do not merge. But what if we were wrong? Late 2024 and 2025 marked a turning point in human history. As data poured in from the James Webb Space Telescope, specifically from the deepest, oldest corners of the universe, something broke our standard models. We looked back to the dawn of time, expecting to find the first primitive stars or baby galaxies. Instead, we found anomalies. The data revealed objects that defied classification. They were too bright to be normal stars, too compact to be galaxies, and far too old to be the black holes we understand. The scientific community was left scrambling for an explanation. The boundary between a star and a black hole had not just blurred, it had vanished. We're no longer talking about theoretical possibilities. We're talking about hard evidence discovered now. We're talking about an object where a supermassive black hole doesn't just eat a star, it wears the star like a suit of armor. It is called a black hole star, a hybrid monster where the event horizon is hidden deep within a shell of gas, powered not by fusion, but by the sheer violence of gravity. In this video, we're going to dive into the discovery that shook astrophysics in 2025. Forget everything you know about how a star is supposed to look. Welcome to the era of the black hole star. It all started in the summer of 2022, shortly after the James Webb Space Telescope opened its golden eyes to the universe. As the first deep-field images arrived, astronomers noticed a peculiar pattern lurking in the background of the early universe, mere hundreds of millions of years after the Big Bang. The images were speckled with extremely compact, point-like objects. They were faint, mysterious, and intensely red. The scientific community quickly gave them a name that sounds almost innocent: little red dots, or LRDS. But don't let the name fool you. These objects were invisible to the Hubble telescope because their light had been shifted deep into the infrared spectrum by the expansion of the universe. Initially, scientists tried to force these objects into the standard models we already knew. Two leading theories emerged. The first theory suggested they were dusty star-forming galaxies, compact factories of stars hidden behind thick curtains of cosmic dust. The second theory proposed they were dusty active galactic nuclei, or AGNs, supermassive black holes feeding on matter, but obscured by a dense donut-shaped ring of dust that blocked visible light. For 2 years the debate raged, but as we moved into 2024 and 2025, detailed spectroscopic analysis shattered both theories. The data presented a paradox. These objects were far too compact to be galaxies. In the telescope, they looked like single points of light, just like stars. Yet their energy signature didn't match a standard quasar either. We were looking at something that had the compactness of a star but the brightness of a monster. The universe was hiding a third option, and to find it, we had to look at one specific object that broke all the rules, an object with the codename Ruby's UDS 154183. The mystery of the little red dots wasn't solved by a photograph but by a fingerprint. To find the truth, we must zoom in on one specific anomaly, an object formerly known as Ruby's UD-154183. But the astronomers who analysed its light gave it a much more dramatic nickname, the Cliff. Its light has travelled nearly 11.9 billion years to reach the James Webb Telescope. When scientists analysed its spectrum, its rainbow of data, they were looking for a specific chemical signature called the Balmer break. In standard astronomy, this is a well-understood phenomenon found in aging galaxies. It usually appears as a gentle step down in the data graph, signalling that giant short-lived stars have died out, leaving cooler older stars behind. So, scientists expected a slope. Instead, with this object, they saw a vertical drop, an absolute precipice. The light intensity didn't just decrease, it crashed off a cliff edge at the ultraviolet limit. This was the smoking gun. Why? Because no collection of stars can create a spectral drop that sharp. A galaxy is made of billions of stars, all moving at different speeds. Their combined light naturally smooths out any sharp edges. But the cliff was razor sharp. This proved, mathematically, that we were not looking at a galaxy. We were looking at a single point source object. So, if it's not a galaxy, what creates such a terrifying shadow? The 2025 analysis revealed the chilling answer. This cliff is caused by an incredibly dense cold envelope of gas, a cloud so thick that it ruthlessly absorbs every single photon at that specific wavelength, creating the vertical drop. And for a gas cloud to remain that dense without collapsing, it must be pushed from the inside by a monstrous source of pressure. This spectral cliff was the final proof. We had found the missing link, a supermassive black hole screaming with energy but suffocated under a blanket of gas. The black hole star. Now that we have the evidence, we must face the reality. What exactly is a black hole star? To understand this monster, we have to perform a cosmic autopsy and invert everything you know about stellar physics. In a standard star like our Sun, existence is a constant tug of war. Gravity wants to crush the star inward, while nuclear fusion in the core creates outward pressure. It is a delicate, elegant balance, but a black hole star is not elegant. It is violent. At its heart lies a seed of darkness, a supermassive black hole. But this isn't floating in empty space. It is buried deep within a colossal envelope of gas, massive enough to form a small galaxy. Gravity, relentless as always, tries to crush this entire gas cloud into the singularity. But here is where the physics gets terrifying. As matter falls towards the black hole, it doesn't just disappear, it spirals in at near light speeds, forming an accretion disk hotter than the core of any normal star. The friction in this disk releases an apocalyptic amount of energy. In fact, this process is far more efficient than nuclear fusion. While the Sun converts only 0.7% of matter into energy, this gravity engine converts up to 40%. This energy screams outward as a torrent of high-energy X-rays and ultraviolet radiation. But remember the cliff from the previous chapter? The surrounding gas is so thick, so incredibly dense, that this light cannot escape. It gets trapped. The radiation slams into the inner walls of the gas cloud, pushing them outward with incredible force. It literally inflates the gas envelope like a titanic balloon, fighting back against gravity and stopping the cloud from collapsing. So, what happens to that trapped light? It slowly struggles through the dense layers of gas, losing energy and cooling down over millions of years. By the time it finally reaches the surface and escapes into space, it has shifted from deadly X-rays to a dull, deep red glow. This explains the mystery. This is why James Webb sees a little red dot. We're looking at the cold, swollen skin of a beast, hiding a blazing inferno inside. It is the ultimate cosmic paradox, a star that shines not by creating elements, but by devouring its own heart. To understand why this discovery changes history, we must look at the impossible early black hole problem. James Webb spotted black holes millions of times heavier than the Sun, mere 400 million years after the Big Bang. According to standard physics, this should be impossible. There is a cosmic speed limit for how fast a black hole can grow, known as the Eddington limit. Normally, if a black hole eats too fast, the radiation it spits out pushes the food away, stopping the meal. It is a self-regulating diet. But black hole stars provide a back door to break this rule. Because the black hole is buried deep inside a star, the radiation cannot escape into space to push the matter away. It gets trapped by the gas envelope. This allows the black hole to feed in a mode called super-Eddington accretion. It feeds without limits, growing thousands of times faster than normal. These red monsters are not just anomalies, they are incubators. They are the seeds that grew into the supermassive giants we see at the centers of galaxies today. Before we conclude, there is a crucial distinction we must make. If you are a fan of astrophysics, you might be thinking, wait a minute, haven't I heard this before? Isn't this just a quasi-star? The answer is a definitive no. And understanding why is the difference between science fiction and science fact. It is easy to confuse the two because they sound similar. Both are black holes hiding inside gas shells, but physically, chemically, and historically, they are completely different beasts. To avoid misinformation, we need to draw a sharp line between the quasi-star of theory and the black hole star of reality. First, let's talk about time and era. Quasi-stars are hypothetical objects from the very beginning of the universe, the population 3 era. They were thought to form from the direct collapse of pristine, pure hydrogen and helium clouds before galaxies even existed. They are ancient ghosts of a pre-galactic age. In contrast, the black hole stars BH, discovered by James Webb, exist much later, at high redshifts, where Z is about 3 to 10. They don't form in the empty void. They form deep within the dense, crowded centers of early galaxies where gas is concentrated. Second, let's look at scale and size. A theoretical quasi-star is truly titanic, a single object as large as our entire solar system, stretching out to 10 billion kilometers. The black hole stars we found are different. They are compact. While they are massive compared to a normal star, they are far smaller and denser than the giant puffy quasi-stars predicted by theory. They are highly compressed engines of destruction. But the most important difference, the one that changes everything, is evidence. Quasi-stars have never been seen. They remain a mathematical hypothesis, a what-if scenario on a chalkboard. We have zero direct proof that they ever existed. Black hole stars, on the other hand, are real. The object Ruby's UDS 154183 and the spectral cliff we discussed are hard, physical data. James Webb has captured their light. We're no longer speculating about what could exist. We're analysing what does exist. So while the concept is similar, a black hole wearing a star, nature has proven it in a different way than we expected. These aren't the primordial giants of the first days. They are the evolved, dense, and terrifying hearts of the first galaxies. This discovery takes a cool, theoretical idea and cements it into the concrete history of our universe. James Webb has only been operational for a few years, yet it has already rewritten the first chapter of cosmic history. The discovery of black hole stars teaches us a humbling lesson. The universe is far more creative and far more terrifying than our models predicted. These little red dots are not just oddities, they are the missing link. They explain how the monsters at the centre of our galaxies were born. They bridge the gap between the first stars and the first black holes. We used to think of stars and black holes as mortal enemies, one light, one dark. But now we know that in the chaotic dawn of time, they were one and the same. As we continue to peer deeper into the void, one question remains. If a star can be a black hole, what other impossible things are hiding in the dark waiting for us to open our eyes?